Space complexity analysis of a program is the analysis of how the memory required or the memory consumed by a program grows with the input. So let's try to analyze the space complexity of recursive implementation of Fibonacci sequence. I will write down the sequence here for you. The first two elements in the sequence are 0 and 1, and all other elements are sum of previous two elements, and we have seen this quite often in our previous lessons. And let's write down the program to calculate Fibonacci sequence. So we have a method fib of n that gives me an element in the above sequence, and if n is less than or equal to 1, we simply return n, else we make two recursive calls to calculate fib of n minus 1 and fib of n minus 2, sum them up and return the result. Now space complexity analysis of a recursive program can be really tricky because a lot of things happen behind the scene, and we really need to understand that how a recursive program executes in the memory to understand and analyze the memory consumption. Now let's say what we have drawn here in the right is computer's memory, and these partitions in the memory are basically some units in which the memory is divided. Now I want to calculate fib of 5. So in a typical program we will have a main method, and from this main method we will call fib of 5. Now let's roll back a little bit. When a method is executing, it is currently in the memory, so all the local variables and information about the method is already in the memory. Now when this method A makes a call to another method B, so for example in this case main makes a call to calculate fib 5, and I will write f5 as shortcut for fib 5 because it's easier for me to write. Then what the computer says is that, hey, I will save the current state of execution of this particular method, kind of pause it in the memory, and go ahead and calculate f5, and then once I'm done with f5, then I'll come back to the main method. So now f5 is executing and it's in the memory, and the main method is kind of saved in what we can imagine to be a paused state, and this is executing. Now f5 is executing, and now f5 makes a call to f4, and this is a recursive call because the function is calling itself, though with a changed argument or a reduced argument. So a recursive call is not different from a function A calling another function B, except for the fact that here A and B are same, but in terms of execution separate memory and resources are allocated to the new function call. So now f4 is executing and the computer has saved the state of f5 as well, and let's say this red arrow here points to the currently executing function while rest of the function are in paused state. Now f4 again makes a call to f3, f3 again makes a call to f2. Now I'll do one thing here, I'll change the color of main method. So rest of the structure in blue is what we can call the recursion tree corresponding to the call fib of 5. So now f2 makes a call to f1, and now f1 is executing. So as we can see here, even though explicitly we have not declared any variable or used any memory in the method fib of n, behind the scene all the states of these methods are being saved in the memory, or these functions calls are getting stacked in the memory and space is getting consumed. We often say that an implicit stack is growing in the memory, and we also call this function call stack. So as we can see here that above this main method from f5 onwards, the growth of the stack has been because of recursive calls of the method fib or f. So in this part of the call stack is kind of the memory consumption by our recursive algorithm. Now in this recursion, f1 does not make any further function call or any further recursive call. It simply returns 1, and now f1 has finished and it also gets popped from the memory, and the control goes back to F2. Now F2 at this stage makes another call to F0, and F0 also simply returns 0 and finishes. And I will rather name this stack as function call stack. Now F2 adds up these two values 1 and 0 and returns the sum to F3, and now F3 resumes again, and now F3 has got F2, so it makes another call to F1, and this pushing and popping into the memory goes on. So now F4 has resumed again, and F4 has got the two returns, so it simply adds them up and returns to F5. And now F5 resumes again, and F5 now has got return from F4. At this stage it makes another call to calculate F3, and F3 again calls F2, and now F2 is executing, and F3 goes in a paused state. F2 again makes a call to F1 and F0, which simply return 1 and 0 respectively. And I'm skipping showing this F1 and F0 in the stack here. Now F2 sums up these values and returns to F3, and F3 resumes again, and F3 again makes a call to F1, which simply returns 1. Once again I'm skipping showing the push and pop in the call stack. And now F3 sums up these two values and returns to F5, and F5 resumes again. F3 simply finishes and is removed from the memory. Now F5 sums up these two values and returns to the main method, which is its caller. And finally main method resumes, and at this stage we have the output from the function call fib5, and it could print the output or use it for some other calculation. Now I'll replace this figure here with an actual recursion tree with all the function calls. So this is our recursion tree. Now the space consumed by this particular recursion was the memory that it consumed in the function call stack, and the maximum growth of this call stack due to this particular recursion was when we were at this particular node, the bottommost node. So when F1 was executing, then all these states of F5, F4, F3 and F2 were saved in the memory, and we were consuming kind of 5 units of space in the memory, and the call stack did not grow any larger than this. So this was the maximum space consumed. And if you analyze it well, then the maximum space consumed by a recursive program is proportional to the maximum depth of this recursion tree, and the maximum depth of recursion tree is defined as the length of the longest path in the tree. So if this is level 0 in the tree and we go down by one arrow, then this is L1, which is level 1, and then we go down by another arrow, so it is L2, and we go on like L3 and L4. So the maximum depth in this case is the path from L0 to L4, which is 4 units in this case, and the number of function calls in this path is 5 units. Sorry, the number of function calls is 5, and the maximum memory consumed is 5 units. If we would have called the function fib for any generic value n, then the maximum depth of the recursion tree would have been n minus 1 units, and the maximum space taken would have been n units. So when we analyze complexity of programs, we often take the upper bound for the time or the space taken. In fact, we most often take the upper bound for the time or space taken. So in this case, the space or memory consumption is proportional to n, and we can also say that this is big O of n in terms of space complexity. In general, the space complexity of a recursive program would be of the order of max depth of the recursion tree. So this was space complexity analysis of simple recursive implementation of Fibonacci sequence. Thanks for watching.